Day 28, Honors Projectile Motion, Problem 10. Starting over here, here's my diagram for Part A. So this red thing is supposed to be the balloon. It's going to be thrown upward. We don't care about the person throwing it. We're assuming it's starting at, say, a ground level. It's going up to a high point, and it's coming straight back down to the same spot. So there's my diagram. That's what I would like you to do on these problems. Draw your diagram. This is technically not a projectile. Well, it's a projectile. It's an uninteresting projectile in the sense that it has no horizontal motion, so I don't have anything over here in this column for horizontal because it's just going straight up and straight back down. So all I have to worry about is the vertical part of the motion. And I'm labeling my point A and point B. That's what you do in projectile motion. You label your point A where you're starting. It's typically the location that they indicate in the wording of the problem. But you do have a choice on point B in this problem. You can pick point B up here at the top like I did, or you could have picked point B down here on the final landing spot. Either way will work this problem. I have the other version worked out on the written hints. But if I pick point B up here, then I label my 5 quantities. The VI is what I'm looking for. Here's the key to the problem. If I pick point B at the top, my VF is 0 meters per second because it stops vertically moving at that location. The acceleration is still negative 9.8 at all times. Just FYI, if you would have picked point B down here at the bottom next to A on landing, your V sub F would have not been 0. Your V sub F would have been negative V sub I. You can do the problem that way, but this is probably a little bit easier. So I picked point B at the top. It's always a good point to pick. You don't always have to do that, but so that gives me the 0 there. Here's the other key to this problem. The time is 2.05 seconds. Now, how did I get that? Because the problem says at the very top, the time is 4.1 seconds, way up here at the top. Well, that's the round trip. That's the time it took to go up and come back down. And without air resistance, these problems are symmetrical in the sense that it takes half the time to get up, so half of that is 2.05, and let's just do 3 sig figs on the homework here for now, even though it breaks the rule of 2 sig figs to start with. I'll let you go to 3 sig figs. If you want to put 2.1 down here, you can, but don't go to 4 sig figs. Anyway, half of 4.1 is 2.05. That's the time it takes to get up, and it's also the time it takes to come back down, but I don't care about that right now. But that's the key to the problem. If I have that and the 0 here, I have 3 quantities that can be plugged into this equation. That's our first of the 4 uniform acceleration equations, and that then can solve for V sub I. You plug that in and show the work for that on your paper. V sub I comes out to be about 20 meters per second if you go to 2 sig figs. So that's V sub I. Part A. Part B then, you're launching the same projectile like this diagram here, and we're trying to figure out the range S sub x, how far it goes down horizontally. So now this truly is a simple or a straightforward projectile problem. The key that students get hung up on is this. The time is not the same. It's not 4.1 seconds. The angle is 45 degrees now, so the launching velocity is 20 meters per second. That's what you solve for in part A, but you're not launching straight up. You're launching at an angle. So the components of the motion, here's one of the keys. This component, V sub x, is not 20. The horizontal motion component is not 20 meters per second. If you do the math there, it comes out to be 14 meters per second. And it's a 45, 45, 90. So the vertical component of the velocity is also 14 meters per second. So if I go now to my standard format that I would like you to use for solving projectile problems, you lay out your horizontal components of the motion. In this case, we know it's moving sideways at 14 meters per second the whole time. We're looking for S sub x, the horizontal range. The time is not 4.1 seconds. It's not going to be up in the air as long as it was when you shoot it straight up. So that's a common mistake made here, because the determining factor for how long it's in the air is the vertical component, way over here on the right, the vertical component of its velocity. This 14 is really what determines how long it's up in the air for. For example here, once again, in this problem, you have a choice of where to pick point B. I picked point B right here at the top of the projectile's motion. It's still moving sideways at that point. I could have picked point B way over here on the far right landing spot. There's another solution on the written examples of how to set the problem up that way. But I picked point B up here. And if that doesn't work for you, try the other spot down here. But in this case, this top spot works because the vertical velocity at that top spot is indeed 0 meters per second. It's still moving sideways at the 14 meters per second, but the vertical velocity component is changing at a rate of negative 9.81 meters per second squared. It's always accelerating in the vertical component. That's the vertical part of the motion, which is independent of the horizontal motion. So now I know the launch velocity vertically was 14 meters per second. The final velocity at that top spot at point B, that's labeled, is 0. So now I have 3 of the 4 quantities, and I can figure out S and T. The main thing I want to know is T, how long it took to get to that top spot. And it's less than 2.05 seconds. You can check it out. But bottom line, I think you're going to use the same equation again, this one over here, show the work for that, and figure out how much time it takes to get to point B. Once you have the time it takes to get to point B, you have to double that and put it over here, because that's halfway through the motion of this projectile. From point A all the way over to here takes twice as long as it does to take from point A to get halfway across the field of motion here. So say T comes up to be 1.5 seconds so when you calculate this over here for the vertical motion getting to point B. Then you have to put in 3 seconds right here for this time. And then once you have that 3 seconds, or whatever it is, it's not going to be 3, well, it's going to be around 3, then you can use V equals S over T to get what you're looking for, the range.